Hello and welcome back to Gaming Like It's 1979. We're going to continue our adventures with Turing Complete. So we have completed the working computer and we're going on to programming. Storage cracker. We need a program that can recover the passcode of a storage room. The easiest way to find the passcode would be to try all combinations until you find the right one. Although the broken mechanism does make a weird beep when your guess is too high, you might be able to use that to your advantage. You win this level when you output the correct passcode. No output will fail the level. Additionally, the input will be 1 after a guess that was too high and 0 otherwise. One interesting thing here is does not indicate how many digits the passcode has. I assume the implication here is since these are 8-bit registers, or I guess 7-bit registers, it's going to be between 0 and 127, right? So our simplest way to do it, right, the inefficient one. What's this? Is this the name of the program? What does that do? New program. Bad safecracker. Let's do a terrible safecracker, right? We're going to put the value, we don't need to do the value, I'm going to put the value 1 in register 1. Right? Reg 0 to Reg 1. Then we're going to output Reg 3. That will be either correct or incorrect, doesn't matter. We're going to brute force this. My first attempt at this is going to be brute force. Okay, then we're going to copy R3 to R2. Then we're going to add. Then we're going to copy R2 to R3. No, we don't need to because now the result is in R3. We're going to put Reg 3 to out. And now we need to be looping. So where is our loop? I guess I should have learned how to do conditionals, huh? I'm assuming that this is the memory location. If that's wrong, well, we'll find out. Okay, so now I need a jump instruction. I think we want to just jump unconditionally. So that's going to be always. Is all 3 of those? No. $196. $196. Give it a nice assembly language name. All right, so this should be, I think, our brute force safecracker. Let's try it. I'm assuming this only goes up to 255. Looks like it might have passed that first test. Okay, so how could we do this a little more efficiently? I'm not actually going to write the more efficient version of this right now, but we know that we're getting an input of 1 from whenever we're too high. So logically, the thing to do would be to start with the highest possible value, I guess 255, and start going down. So try the highest value. If you get a 1 in the input, divide it in half, I would say, or a quarter, whatever you want. And then as long as you continue to get a 1 signal, continue dividing it in half. And then once you get a 0, then you have a different state for your machine where you're going to be, counting up by a certain amount. That would be probably my first crack at this. But since this is a let's play and we're just trying to get through the levels, I think we should declare victory and move on. And plus, I don't want to make life too easy for these pesky aliens. masking time. The length of our week is 4 days. Our weekdays are named 0's Day, 1's Day, 2's Day, and 3's Day. I hear some Earthlings number their Tuesdays incorrectly. Anyway, New Year's coming up, and we want you to calculate the weekday of everyone's birthday. We will give you the date, and all you have to do is return the weekday within 8 ticks. Alright, so the hint here is in the name of the level, which is masking time. So we need a portion of the input that corresponds to the rightmost 3 bits. 0, 1, and 2. Alright, so how do we do that? Well, I think first off, I did not expect that to happen. I think first off, we want to move the input to our register 1 because we are going to have to do some math on it, right? And then we want to mask that input with the rightmost 3 bits. And the rightmost 3 bits are 1, 2, and 4. Add those together, we get 7. Right? That's a bit pattern that looks like that. Right? That's 7. So we're going to want to make a new input here. It feels like wherever I put my face, it's in the wrong place. Let's move it over there for now. Okay. Zoinks. All right. Okay, we're going to do input to R2. I think that is R2. We're going to call that. There we go. Okay, if that's wrong, we'll find out. Oh no, I don't want input to R2. What am I doing? I'm being dumb. We want to put that in register 2. Okay, then we want to mask them, and that's just doing an AND. That's a condition. Compute. Add sub. Rightmost 2 bits. 67. Okay. So that's AND. Now they said I have 8 cycles to do this within, right? And we've already used up 4. So at this point, what we would have is the rightmost 3 bits, and we want those to be equal to 4. So first of all, they're in the wrong place. They're in register 1. Oh, I wanted that to... I keep wanting that to just input. Not to just actually make that work, but register 3 to reg 2. And then we're going to... Oh, we mask out those right to... We just want to know if it is... First of all, is 0 mod 4? No, that 4-bit will always be true, I believe. Well, we'll find out if that's wrong when we run our tests. We want to know if this is equal to 100. Because anything else will not be mod 4. So 100 is 4. Right. I feel like we've already blown the budget. And at that point we need to do... Oh, this is tricky. Oh, wait, so... Okay, that's great. I was worried that we were going to have to return, you know, some true or false value. But really, We're just returning that number mod 4. So really, I think what I started off doing here, I think that, isn't that our number, mod 4? And so we just need to put it out. How is that not the right answer? Well, let's try it. So our input is 28, and there it is. Gonna walk through. And we gave the wrong answer. 28 mod 4 is 0. Oh. Okay, so to get mod 4, we're left with that. What we actually want is to calculate the remainder, I think. So there's a subtraction that has to happen here. Okay, so at this point, and so now I put that in register 2. I think that's right. And so we want to put 4 in register 1. We want to subtract, and I do not have a subtraction sub. 69. I'm not saying it. I'm not saying it. Okay. And now we can do reg3 to out. That looks like 7 ticks. Let's try it. Oh, and this is cute. We can basically see our registers here. That's pretty great. Okay, so 28 went into register 1. 7 went into register 0, is then copied to register 2. We then get the AND out of that. We do a subtraction, and it did not work because we did not copy it. We did not copy these things to the right place. Let's take another look. Because AND goes to register 3, so we need to actually copy that into okay. I think that should do it. Okay, 4 gets copied. We get subtraction, and I think that worked. I think that, ooh, so what happened? Ticks left 0. So in this case, did we run out of time? No, it's saying 173 mod 4 is 1, and we gave it 255. How did we end up with 255? Well, let's go till we get 173. So here's 173. Okay. 173 is in register 1. 7 is in register 2. Let's bring up our program. I like this view better. Okay, then we're going to AND, and the result goes into register 3, which is 5. Did I simply, I think I'm inverting where these things are. I'm doing the subtraction backwards and thus ending up with a negative number. So I think if I just change these around, and I don't have an R3 to R1, so I need to create it. And once again, I've forgotten copy register 3 to register 1, 153. Maybe I'm overthinking this. By the same logic, couldn't we simply AND this again and mask off the 4-bit? If it were 4, then masking it off would leave a remainder of 0. If it were 5, masking it off would leave a remainder of 1, which is correct. If it were 3, as in this case, masking it with... Does that actually work? If it's 3, we want the remainder to be 3, and it would be. So if we just mask this with 3, does that do it? And have I masked this too much? So let's do this again. So we're going to make 3 our constant, and then we're going to AND it again. Does that work? I feel like that works. Let's step through. Okay, so there's our 4 remainder. We're putting 3 in register 2. We're doing AND. We get a remainder of 0, and that works. Okay, so now we're getting 173. We have a remainder of 5. Yep, and that leaves us... Yeah, I think this works. All right, wow, that was easy. No subtraction necessary at all. Took a little detour there, but we got there in the end. All right, so shooting the space rats. After playing with this for a little bit, I think I have a plan. The plan is there's going to be 2 phases of our program. The first phase is going to be our setup phase, and the second phase is going to be the shooting phase. So the setup phase involves going 2 to the right, then going up 1, 2, 3, 4, 5, and then that's it. 2 to the right, up 5. At that point, we wait, and we wait every turn until we see a space rat, which is, it looks like, value 33, and then we shoot. And then we continue to wait, and that's the loop until the end of the program. I think that will get us there. So let's try and actually implement that now. And let's make ourselves a comment so that we know what we're doing. Move right twice. Move up 5 times. That's a loop. Wait until we see 33 and shoot. That. Okay, so we're going to turn right. Then we're going to move forward twice. And I think we can just leave it like that. Then we're going to turn left. Then we're going to move forward 5 times. Now, if I recall correctly, what we see is going to be coming in via the input, right? And we want to do a comparison. And for the comparison, I believe we're comparing against what is in register 3. So once again, we're going to need a new value, and that's going to be 179, I think. Input to R3, right? So, input to R3. Then we need to compare this against 33. Well, so we could cheat. And in fact, I'm inclined to cheat. So the proper way to do this would be to actually do a comparison against 33, which would involve putting this in register 2, putting 33 in register 1, subtracting it, and checking that it's 0. I don't know whether these monsters are going to move on our cycle. What I do know is that for this specific problem, really all I care about is that the value that I'm seeing is not 0. So I think I can just compare that it's greater than 0. So I'm going to need to check our instructions. It's going to be a condition. Let's do condition not equal to 0. So that's 197, huh? Okay. So we'll call that jump not equal, or jump not 0. JNZ, why not? So now we will, let's set up our label. You know, if there is a label for our assembly language, I've somehow missed it. I'd really love to be able to say, you know, like that. But for right now, let's just pretend there isn't. And if there is, someone can leave a message down in the comments and educate me. So we're going to put that input to R3. Nope. Right. And then we're going to say jump if not 0. And then we're going to shoot. Nope, sorry, I'm wrong. I'm wrong about what we're doing. Okay, I think that the start of our loop has to be a wait directive. That's what I think. So this can't be here. For reg 0 to out. Now we've waited at least once. Now we could put 13 there. Copy the input to R3. Jump if it's 0. If it is 0, then we're going to wait again, and that'll be okay. And if it's not 0, then we want to shoot. And at that point, we just want to jump back to 13 and keep shooting. I think that's our program. Let's see how well or how poorly we did. Well, first let's step through our setup phase. Something's not right here. What am I doing wrong? Well, somehow I broke everything. Let's go back out to the level map and come back in. Will it work now? There we go. Some weirdness going on here. All right, well, I have a bug. So why do I have a bug? 0 into the register. Oh, I must have the opcodes wrong. I think this is actually 1, this is 0, and then this is 1. Let's try that again. Turn right. Now it's working. Turn left. 1, 2, 3, 4, 5. Okay, now we're in our loop. We're going to wait. We're looking to see if we see anything. We don't. We wait again. And now we should. Nope, we're not doing it. Oh, I got this exactly wrong, exactly backwards. This is the story of my programming life. I don't want to be jumping when it's not 0. I want to be jumping when it is 0. Well, JNZ is a pretty good opcode to have, so we're going to leave it. 193 is going to be jump if equal to 0. So that 193. Call it JEZ. I've also seen this called JEQ, but I like JEZ. All right, try this again. Do our setup. It's all good. Are we actually shooting? We are. Okay, so that's great. That implies to me that our various... Well, let's take a look. Let's step through slowly. We waited. We grabbed our input. We did not jump. We did jump, rather. Now we're waiting. We grab our input. We do not jump. We prime our gun. We fire the gun. At that point, we jump back. We did not jump back. Maybe it's just a bug in how this thing is displaying it, because it did eventually get back there. Oh, and then we're waiting again. That's why. Having the wait at the beginning of this loop is challenging. So how can we do this with the wait in a different location? We can put the wait at the end of this loop. So this is 12. No. Is it still 13? No, it is line 12. And that's still going to be where we go when all is said and done. But then, okay, so this next one should be a shot. Okay, we're getting our input. There's 33. We're not jumping. We're going to shoot. Right, if we shoot, then we should not be waiting. That's the description of the problem here. Okay, after going back and actually reading the documentation, it turns out there is a label opcode, and it is, you're going to be shocked, label. Okay, we'll call it label loop. If it's 0, call that wait. That's our label. Okay, so I think we can just use these labels like so. So this is the wait label. We're going to wait and do whatever. And this is going to be loop. If we have fired, then we're going to jump back to loop. Correct? Correct. We can also use constants, which would have made this a lot, I would have avoided quite a few mistakes if I'd used constants here. So let's, why don't we do that? All right. All right, so now with our labels, let's think about it. We've got a label. We're grabbing our input. And you know, I think there's no reason why I shouldn't have these like that. Right, zero it out. All right, let's see how bad this is. And that makes it a lot easier. Wonderful. Whew. Boy, that level gave me much more difficulty than I would like to admit. And part of it is that I'm still treating this like a game rather than like accepting that I need to get my head into that assembly language programming space where you are very rigorous about how you approach problems. Lesson learned. Next program I write with this, going to use a lot more constants and labels. All right, the last level in the programming section of the game. It's called the maze, the fabled maze. Remember, you can't use immediate values larger than 63, which can affect our jumping. Okay, well, let's go. And right off the bat, I want to make sure that I capture these constants. And the nice thing is these don't use any memory. Amusingly, last level, I used the constant 4 rather than 3 for do nothing, and that's wrong. 4 is actually a use action. It happened to work okay, but oops. Okay. So what do we want to do here? Looking at this maze, it is a simple maze. There are no multiple exits or anything like that. There's one exit. I don't know if these things are traps or if these coins matter at all. That looks like the exit. So what we're going to do is we're just going to follow, I think, the left wall. And we know we're starting facing up, so I'm going to go ahead and initialize this as preparation. All right, we're going to turn left, and then the real algorithm starts there. Now, what is the real algorithm, right? Well, you know what? Let's make a label. What is the algorithm? It's going to be move forward. Can I move forward? Yeah. Then we're going to turn either left or right. If we see a wall to our left or right, then turn back to the right. I think we also need to use the door handle if it's there. And I think it's safe to use it if it's not there. Hopefully that won't cause us to get killed. And then do it all over again. That sounds right. I'm sure there's a bug here that I'm just not seeing yet. We'll try it and we'll see how it goes. All right, so we've already done our initialization. So our first thing we can do, and I've already made a mistake. Right. First thing we're going to do is move forward. And that's how we actually implement that. Then we're going to turn left. The other nice thing about using constants is that if I have made a mistake in these constants, I just have to fix it on that one line, and the rest of my program should still be valid. Okay, so now I've turned left, and now I have to check whether there is a wall in front of me. 2R3. Wall is 1. So here we cannot cheat like we did in the previous level, because there are objects here. In fact, let's go make sure that that is the case. Can I go here? Wall. Right, so we have these objects like coins that are going to have different numbers. And we've got that. Using the coin doesn't do anything. Of course, the coins are all at dead ends. Maybe it's okay. Will it be okay? Let's walk through our algorithm. All right, so we were saying move forward, turn left. There's a wall, turn right. Wall, turn right. I'm skipping the use part. Okay. There's a wall, turn right, move forward. At this point, we would get stuck forever. So we probably need to turn until we don't see a wall, right? And that'll handle the corners, I think. So wall, turn right. There's no wall, so we don't turn right. We go back to the beginning. There's a wall, turn right. There's a coin. If we say that it's simply any non-zero value, then we can do that, right? Turn left. There's no wall. Yeah, I think we can say if it's any non-zero value. I want to try it because that'll save us doing some math. It'll make it a little more efficient, I think. Okay. So now we are turning left. We've walked forward. We've turned left. We're testing to see if there is a wall. Let's give our labels capital letters so we know they're labels. Okay, input to R3. If it is non-zero, right? Then we're going to right. No, this is wrong. This is totally wrong. Right, if it is 0, then we know we can step into that space, and so we can start over. If it's not, then we will continue on, at which point we should try to use whatever it is, just in case it's a door. Then we're going to turn right. Nope. And then we're going to jump back to check wall. We're going to do it again, I think. Unconditionally. I've surely made mistakes here. I'm curious to see how badly this goes wrong. Let's find out. Very badly seems to be the answer. And in fact, it looks like there's nothing in the... Do I need to close this panel before I get the program? Ah, we have an error. Need a name and a value after a constant. I've got it completely backwards. That error was staring me in the face for the past 10 minutes while I typed, and I didn't pay any attention to it. All right. Okay. Trying it again. And boy, does that fail. What am I doing wrong here? So I thought I was turning left, but it clearly turned right. Did I get the robot commands? Okay, that looks much better. Let's see if our little robot can find its way to the exit. People have asked me, am I embarrassed that I make so many mistakes when I'm writing programs or playing these games? And I'm really not. For me, mistakes are part of programming. They're how I learn. And so if I screw everything up while I'm doing it, that's par for the course. Oh, wow. Okay, so we've gone on to a new level here. And I see that there are other elements in this level. So now I'm wondering if at some point this invariant that I kind of am relying on, that the coins are always at the end, I wonder if that's going to fail me. I may jump to the end here. If this succeeds, I'm going to cut to the end rather than making you watch the entire session run. Looks like I can make this go faster too. Let's do that. If I've erred, we'll get to the error very quickly. There we go. That's much more exciting. Last test. That's it. And we have now finished the programming section of Turing Complete. I don't know what comes after this. Let's find out together. If you choose to go on to the rest of the levels, I will teach you about RAM, the stack and function calls, and you'll get to solve more interesting challenges like this one. But first, you would have to build a better computer, and we're going to get another architecture. That's great. So we have not been eaten. We have beaten the basic parts of Turing Complete. Let's take a look at where we've been. We've built a bunch of circuits and components, and then up ahead we've got CPU architecture 2. This must be the leg computer they're talking about. We've got functions and then some assembly challenges. Well, yeah, I don't know if you want to see me solve more of these things like a dancing seal. We could just say we've escaped from the clutches of the aliens and are no longer eaten, and we can stop here. If you are enjoying this series and would like to see more of them, if you would like me to go on to CPU Architecture 2 and Friends, please leave a comment down below. And, this has been Gaming Like It's 1979. Thanks so much for watching.